and aluminum. Now it's also very important to realize that when people repeated this experiment for different light intensities, the result was always the same. So this means the result is independent of the intensity. And this is already saying that the light in this experiment cannot really be treated as a wave. Because if this was true, then the intensity would be proportional to E squared. And then the energy that is transmitted is basically given by E0. But it turns out the experiment says that this is here not the case. Also, the whole experiment was instantaneous. So before people came up with the actual interpretation of this experiment, they thought that all of this effect was due to heating. So this contact heats up and the electrons emit, and this takes some time. But again, the experiment told us that this is not true. So let us now discuss this equation in more detail. And actually what I have done here is I've put these terms onto the other side. So basically this W0. So we have now the Planck constant times the frequency is equal to EU, which is basically a different measure for the kinetic energy, since our current must always be 0. And then we have this material constant W0. So this seems to be the energy of the light. So the energy is used to first emit the electrons from the material, which is characterized by W0, and then the rest of the energy will be used as a kinetic energy that leads to the motion of the electrons. But since this whole term is independent of the intensity, it seems like that the transmitted energy is always coming in portions. And this is also very important if you think about that below a critical frequency, no matter what you do to the intensity, no electrons will be emitted. So this means only one light particle can interact with one electron. So what this means really is that light is a particle. So the transmitted energy comes in portions, and light can be characterized as being a quantum. So this quantum of light, this portion that we have introduced, is also called a photon. And the energy of a single light particle, of a single photon, is the Planck constant h times the frequency of the light. And then people have also introduced a different version, which is h bar, that we will use in the following, and then this frequency, which is actually 2 pi times f. So now we have learned that lights have particle-like and wave-like properties, and in the next lecture we will put everything together and formulate the particle-wave dualism, not only for light, but also for matter in general. Welcome